to this point, we've seen how if we have moving charges or a current, we create a magnetic field, right? So we have a current, the direction that positive charges would flow, that gives us, of course, our magnetic field, like this, our B field. And it loops around this wire. But if we have moving charges that are caused by an electric field, right, that makes the charges move, that creates a magnetic field. The question is, does the reverse happen? And the answer is yes. If we have a moving magnet in certain situations, just like moving charges, then we can create an electric field and a current. And so we're going to look at how this is created. So we need to remind ourselves of the concept of flux. So flux, when we looked at it in the electric field case, we saw it in Gauss's law. So for the electric field, you may recall that the electric flux is equal to this integral E dot dA, right, where we counted up field lines around an area, and that was equal to our Q enclosed over epsilon naught. And this is our electric flux. So similarly, we can talk about a magnetic flux, which would be the integral of B dot dA. So now this is a magnetic flux. Now we don't have an equivalent to Gauss's law in magnetic fields because there are no magnetic monopoles. There is no individual enclosed. Our similar relationship is like Ampere's law when we talk about a loop that's enclosed. But that's not counting a flux. So this is looking at what happens with a magnetic flux. And in particular, we're looking at, it's not so much a moving magnet as a changing magnetic flux. That creates our electric field and our current. So we write the equation. This is Faraday's law. Is that the change in the flux over time is equal to something called the EMF. And we're going to just look at the absolute value. There is a sign that we'll deal with, but that's Lenz's law, and we're going to come back to that. We're just going to deal with this first. So this is called the EMF, which stands for electromotive force, but it's not well named because it's not a force. It's actually a voltage. Okay? So you can write it as a V if you prefer. I'll use the book's notation, which is this curly QE for this induced EMF or voltage. But if you'd rather write it as voltage, just like we get for V equals IR, that's fine, a voltage difference. Okay? So this means that we have a changing flux, changing magnetic flux gives us an EMF. So there are a couple of ways we can change the magnetic flux. Okay, so let's first look at the case where we have a uniform magnetic field so that we can write our flux as just B dot A. Okay, so we're going to look at the magnetic field and assume it's constant over some region. Well, it may be changing in time, but has the same value. It's 5 everywhere across the region, and then it might change to 4. Okay, so that's how we're going to look at it. We're going to say it's uniform, and what I mean by that, it's spatially uniform. Spatially, I can't spell today. It's uniform in space. Okay, so if we have the magnetic flux, the way we can have it changing, in other words, this is what we're looking for, this changing flux that creates an electric field by giving us an EMF or a potential difference. So the magnetic field can change with time. So it can increase or decrease. And so the kind of thing this looks like is when we have a magnetic field, say we have our area, we'll make our area a loop, and we have a magnetic field that is the same So it's not due to this loop, it's just a magnetic field that this is going through. I need an area for this to go through so that I can say that, hey, the magnetic field might be getting smaller or it might be getting bigger. So like these arrows are getting smaller or bigger with time. We're turning the field up or we're turning it down or moving a magnet away, which reduces the field. Okay, the area could change, so I could have a situation, the same situation, where the area that this field is going through is shrinking, right? So you have a ring like this and it's getting smaller. Okay, so it shrinks down in size. So that could happen, or it could get bigger. Heat it up, it gets bigger. So that would be the loop, whatever loop you're looking at, to look for this change in voltage and then have a current, if it's a conductor, gets bigger or smaller. So the loop doesn't have to be round, it can be square. Or the angle between them changes. So that would be a situation where we've got the magnetic field that points like this, right? And I have a wire loop, whoops, like that, and it goes from that orientation. Actually, I'm going to change it just a little bit. I'm going to say it goes from, it goes from that orientation to an orientation more like this. When it's up like that, notice we don't have any flux because the area direction, I guess I should have reminded you of this, the area is just like we've had before. This is our surface, so to find the direction of the area, it's always perpendicular to the surface, to the area that we're interested in. So here I have B is pointing up, A is pointing up, so the angle between them, the dot product, B dot A, is equal to the magnitude of B times the size of the A times the cosine of the angle between them. In this case, the angle between them is 0 and cosine of 0 is 1. Here, in this second situation, like if the area is suddenly in this direction, notice there's area and there's B. Notice we've changed. Now we have B dot A is equal to 0 in this second situation, right? And so if we change from our loop being flat to then rotating, while it rotates, that changes the magnetic flux. So all of those things are ways that the magnetic flux can change, and that will create this voltage. Okay, so that's the general idea. So let's say we have a magnetic field that starts from 0 basically, and it increases like this with time. So this is magnetic field, this would be in Tesla, and this time would be in seconds. And let's say that it's pointing out of the page, so that would mean that as it gets bigger, we would get bigger dots like this. So it's pointing out of the page, it's the same value everywhere on the screen. And so what happens is these dots are increasing. So it might be that we start out with 1 millitesla, so that would be 1 millitesla at some time, and then at some time later, that looks like about 3 millitesla, right? So then we get, if you want, you can think about it, this is bigger dots to show that it's a bigger field. There's not a good way to show that this is a really bigger field. We just have to have this graph. Okay, so these dots are getting bigger, and what happens is then we can calculate the induced voltage. We'll get a voltage difference throughout this ring, and the induced voltage ring, the induced EMF, the EMF, which is a voltage, is equal to the change in the magnetic field times the area, dot the area, in time. So in this case, the area is pointing out of the page or into the page. It doesn't matter. We'll figure out the signs of these things later. And so the b dot dA I can write as the derivative of b times a dt. Now the area isn't changing, so I can pull that out. So this EMF is going to be area dB dt. So the derivative, the change in the magnetic field. So in this case, that would just be the slope, right? Because that is, the slope is the derivative. So if this were, so let's say it goes 3 millitesla in 1 second. So that would be 3 millitesla per second, or 0.003 Tesla per second. And if we put that over here, then our EMF is just going to be the area of this loop times our slope, 0.003 Tesla per second. And the area we would get just by knowing how big this radius is, and that would just be pi r squared. If it's a circle, if it's a square, then we just find the dimensions. So that's pretty straightforward to try to find this voltage, okay? We can do the same thing if the area is changing, and we can do the same thing if the angle between them is changing. So we'll see in some of the examples how we calculate all of those things.